Following the baseline methods, the team successfully implemented a genetic algorithm to develop a machine learning pipeline. A genetic algorithm starts by randomly generating permutations, which are also known as species. For our project, these permutations consist of combinations of pre-processing and classification objects from sklearn library. At each iteration, or generation, each pipeline is trained on the dataset. Depending on which of these species score the highest, certain pipelines will be duplicated with certain parameters adjusted randomly. The lowest scoring pipelines are discarded so that the total number of pipelines remains unchanged. More simple or sophisticated genetic algorithms also incorporate a crossover rate where compatible features of a certain pipeline are mixed for the next generation. With the assistance of a library called TPOT, the team implemented a genetic algorithm to optimize a machine learning pipeline. TPOT is built on top of sklearn, and some of the preprocessors and classifiers that get iterated through are shown here. The XGBoost classifier was also added to this library by creating a wrapper function that calls the training and evaluation subroutines and defines parameters in the same style as sklearn. These settings are shown as well below. One drawback of using a genetic algorithm is the amount of time needed to run each generation. We ended up using just 10% of the data set, and the algorithm was run overnight to maximize the amount of permutations exercised. The best performing algorithm that was developed with the genetic pipeline outperformed all the baseline pipelines and achieved a log loss score of 0.54. This happened to be the same XGBoost library that was tested earlier, and the score achieved what's roughly equivalent to a top 20% score in the Kaggle contest. Interestingly, the best preprocessor appeared to be not pre-processing at all. We believe this is because this particular classifier uses many boosting estimators, so finding the best features will occur naturally, and the heterogeneous data is not an issue. Now, these are promising results since they match what many of the participants found to be the most effective algorithm, but also slightly disappointing because they don't really say anything we don't already know, which is that support vector machines and gradient boosting are pretty good and work almost anywhere. So in order to find something that is actually interesting, the genetic technique was improved based on some techniques we discovered earlier, specifically the stacking algorithm. One thing the TPOT architecture doesn't do is look at stacking methods. However, when the algorithm runs, it trains many different methods, but ultimately throws them away in favor of one that's slightly more accurate. So instead of effectively wasting these already trained algorithms, the team attempted to reuse them in combination with the original algorithm selection. The TPOT approach was modified so that the 4 best algorithms were combined to form a single stacking classifier. Those 4 algorithm types are shown here. The types were kept distinct, and under these new circumstances, the pipeline achieved a score of 0.157, which was our most competitive score and roughly 200 places higher than the original unstacked score developed earlier. This was still not a top 10 or even top 100 place score, but it was considered competitive. Now, work on this project led to several important discoveries about machine learning and some of its real-world applications. First, the job of the data scientist is still very much relevant. In spite of all the attention neural networks receive, setting up and training these networks is not a trivial process, and the finer details of feature engineering are nuanced. For instance, splitting the date into numerical values is a simple job that was necessary for developing a competitive algorithm. However, an algorithm that would develop this feature naturally would be very complicated and not worth the effort to implement. Additionally, the team learned how parameter tuning is an important step in developing a machine learning pipeline. Although gradient boosting support vector machines are an obvious choice for many situations, our original attempts to use the XGBoost library yielded our worst set of results. However, with small adjustments, the algorithm ended up being the best individual learner that we trained. And without iterating through these permutations, we would have likely passed to something else. And so in that regard, genetic algorithms are useful, but support vector machines are always a good place to start from. One of the more exciting discoveries during the project was not only that stacking ensemble methods are commonplace, but they're actually not very difficult to implement. Stacking methods are considered safe because when they're set up appropriately, they will only improve the model's performance and won't be capable of harming performance. And the process of developing a good pipeline in an efficient way would be to simply reuse models you've already trained. In the Kaggle contest, once it was complete, the top 10 finishers all revealed that their predictions relied heavily on stacking. The team may decide to submit a pull request to the Teapot repository that adds this work we've done on stacking methods to the pipelines it's capable of generating. Personally, it's been something very exciting to work with. Also, the genetic pipeline we've developed still doesn't consider neural networks because of how many different parameters there are to train here. But with some better heuristics, these techniques could probably improve the overall performance of our approach. Regardless, the work the team has done here will be useful with any machine learning applications we may encounter later on. Thanks for watching. We hope you found this interesting, and if you're interested, our code is currently hosted on GitHub with the link on the previous slide.